In this video, we are going to learn about a very important and very interesting topic of the data structure that is called as asymptotic analysis and asymptotic notations. But before really going into the topic, I'm going to come back to the question that I gave you as an assignment in the previous video. Let's discuss how to solve that question or how to solve the running time of that question, and then we are going to continue with this topic. So let me just open that question and let's start with how we can find the running time of this code. Okay, so let's first number each and every statement that this function has. So let's start numbering them. This is statement 2, this is statement 3, this is statement 4, and this is statement 5. Now the first statement is going to take 1 unit of time because this is a assignment statement. In the second statement, we have one assignment statement which is going to take 1 unit of time and it is going to run only once. We have these two statements which are going to take 2 unit of time, and as they are the part of the loop, so they are going to run multiple times. We have this j is equal to 0, this assignment statement which is going to run for 1 unit of time, and we have these two statements in statement number 3 or in step number 3 which are going to take 2 unit of time. We have this statement, that is step number 4, which is going to take 3 unit of time, as we have two operations, two arithmetic operation and one assignment operation. So let me write here 3 unit of time. And finally we have the fifth statement which is going to take 1 unit of time. Now, as we have written the time required for execution of each and every statement, let's see how many number of time each and every statement is going to execute. So the first step or the first statement is going to execute only once. The second statement is going to execute for n plus 1 times. So let me write here, this 2 unit will run for n plus 1 times. Now this third statement, as this is the part of this outer loop, so this third statement is going to run for n times. This fourth statement, as it is part of this for loop or the third statement for loop, and also it is part of the outer for loop, so it is going to run for n into n times. So yeah, this is the final time required for execution of each and every statement. So the final step that we are going to do is we are going to sum each and every time that we have calculated. So let's write the f of n function, that is the running time function for this program. So for this program we require 1 plus 1, that is 2 unit, plus 3 unit and plus 4 units. So we need 4 plus, this is 2n plus 2, so let me write 2n plus 2, plus we have 2n, so let me write 2n plus, this is 3n square, so let me write 3n square. Yes, so this is the final expression that has been created. Let's evaluate, or let's shorten this expression. So we have 3n square plus 2n plus 2n, that is 4n plus 4. So this is the final expression, or this is the final input running time for this program. So I hope you all have got the same answer. So let's continue with the topic that we are going to discuss in this video. Let's continue with the asymptotic analysis and asymptotic notation. So before so before diving into the topic, let's take this example. Suppose we have two running time function, f1 of n and f2 of n, where f1 of n is a first running time function and the function is 5n square plus 6n plus 5, and we have another input function, or we have another running time function where the function is 5n square plus 8n. Now suppose the value of n is 2. In that case the f1 of 2 will be 37 and f2 of 2 will be 36. Okay, now let's suppose the value of n is very large. Suppose it is like it is 1 lakh. Okay, so in that case, if we evaluate these two functions, or if we evaluate these two expressions, in that evaluation we can observe that this factor, that is the 6n plus 5 in case of first function and 8n in case of second function, is very negligible. You can observe this. So we have this 5n square plus 6n plus 5. If the n is very large, then this 5n square, this value is going to be very large, and this second factor, that is 6n plus 5, is going to be very negligible as compared to the first factor. Similarly, in case of second function, if we put a large value of n, then in that case 5n square is going to be very large, and this 8n is going to be very negligible as compared to the 5n square. Okay, so this is the problem with running time. If we calculate running time of the program, then that running time is very precise, but when the n tends to, when the n, that is the input size, when it tends to infinity, then these factors play like no role in the running time, or they have very less impact on the program's running time. So that's why we are going to come up with a new method of calculating a running time, and that method is called as asymptotic analysis. Now this asymptotic analysis is kind of extension to the running time method that we have seen in the previous video. So in this asymptotic analysis, what we do is we evaluate the performance of an algorithm in terms of input size. So as in case of running time, or as while calculating the running time of program, we used to evaluate the algorithm in terms of the input size of an algorithm. Similarly, in case of asymptotic analysis also, we evaluate performance of an algorithm by its input. But in case of asymptotic analysis, we don't measure the actual running time. Okay, so here in case of asymptotic analysis, we don't measure the actual running time. So as we have seen in the previous steps, that is calculating running time, we have made all these calculations, or we have calculated running time of each and every step, and we have made all the calculation. But in case of asymptotic analysis, we are not going to do this. Okay, so we are not going to calculate the actual running time of the program. Now when it comes to the asymptotic analysis, we have three types of analysis, or we have three common type of analysis that is generally used in case of asymptotic analysis. So we have base case analysis, we have average case analysis, and we have the worst case analysis. So let's discuss what is meaning of these three types of analysis that we have in case of asymptotic analysis. So let's take an example. Suppose I have an array, and suppose I have some elements in this array. So let me write some random elements in this array. Okay, so this is the content of my array. Now the problem is, so basically I'm going to discuss with you the very famous and very simple algorithm, that is the linear search. So suppose I give you a key, and the key is suppose 2. You have to find whether this key is present in this array or not. Suppose I give you a key and the key is -1. If you can see, the key, that is 2, is present at very first location. So if I give you this key, that is 2, and if I tell you to write a program and to execute the linear search algorithm, in that case it is going to take only 1 unit of time, because this key is present at very first location, and this case, or this ideal case, is called as best case. And in asymptotic analysis, when you are going to analyze the best case, we call it as a best case analysis. In second example, we have key that is -1. So in this case, this -1 key is present at very last location. So in case of linear search, as we all know, in linear search we traverse array one by one. So in this case, to get -1 key or to get location of -1 key, we need to travel the entire array, and this is something which we call as the worst case. And in this case, to search -1 in this array, we need, so in this array we have 0, 1, 2, 3, 4 and 5 as the index of the array, and this -1 is present at the sixth as the sixth element. So in this case, this linear search is going to take 6 unit of time, as this -1 is present at the last location. So I will write here as 6 unit, or in general I can write as n unit, where n is size of the array. And this is something which we call as the worst case. As a programmer, we always hope that the worst case should never happen, but it's the reality, because sometimes all the elements are not going to sit at the first place. So we have discussed about the best case and the worst case. Now the final thing that we have is the average case analysis. Now what we do in average case analysis, uh, so we have this array, we have multiple keys in this array. So we calculate time required to check whether each and every key of this array is present in this array or not. We calculate that time for each and every key, then we sum that time, and then we take average of that time, and that is something called as average case analysis. So it's very simple. We calculate time required for each and every key or each and every possible key of an array. So for this example we have linear search, but it depends which algorithm you are talking about. So in general, we calculate time required for each and every possible input for that algorithm, and then we take average of the time that we have got for each and every possible input, and by that average we analyze the algorithm, and that is something called as average case analysis. Now as a programmer, we should always worry about the worst case, because if we are able to write a program which is going to perform very well, even if the worst case occurs, then that is the best program, or that is the good program. Okay, so as a programmer we should always worry about the worst case. This best case is this best case is truly useless for the programmer. Okay, because best case generally never happens when it comes to running actual programs. So best case is not at all useful for the programmer. Average case is useful, but it is tedious to calculate that, as we have to calculate for each and every input. So as a programmer we will also not consider this average case analysis. So as a programmer we will always consider this worst case analysis, because as I said, if the program is running good, or if the program has good running time for the worst case, then even for all the cases that program will run better, or that program will perform very good. So that's why we should always worry about the worst case. Now let's go back to the previous discussion that we were having. So we have three different case, or three different type of analysis in the asymptotic analysis. Now now to do the asymptotic analysis, we have some asymptotic notations. So to represent running time of the program, or to represent the time complexity of the program, or time complexity of an algorithm, we have some asymptotic notations in asymptotic analysis. Now these notations are nothing but the descriptions that allow us to examine the running time of an algorithm by expressing its performance as the input size. So by using these asymptotic notations, we can express performance of an algorithm in terms of an input size, or in terms of input size of an algorithm. So in asymptotic notations, we have actually multiple notations in this asymptotic notations, but I'm going to discuss about the some of the commonly used asymptotic notations. So we have three commonly used asymptotic notations. First one is the big O notation, second one is the omega notation, and the third one is the theta notation. So let's discuss one by one what is meaning of this notation, and as a programmer, what notations really matter. Okay, so let's discuss about them one by one. So let's discuss about the very first notation, that is the big O notation. This big O notation, or this big O asymptotic notation, is represented by this symbol, that is big O. This notation is generally used to represent the worst case, or to represent the worst case of the program. And as we all know, or as it is a kind of a common sense, that worst case is basically a upper bound for the running time of a program. Okay, so generally, or this big O notation is used to indicate the worst case, and it generally indicates the upper bound of a program. So let's discuss about it in much details. So as I said, it is the asymptotic notation for the worst case. It provides the upper bound for the running time of an algorithm, and it is the most commonly used notation. So as a programmer, we should always worry about the big O notation, as it is the most commonly used notation. Now let's understand the significance of this big O notation. What is the meaning of this big O notation? So basically I'm going to discuss about few programs, or I'm going to discuss how we can find out the asymptotic analysis, or how we can write the time complexity in terms of asymptotic notations in future, in just a few minutes. But let me just explain you how this asymptotic notation works. So let's suppose you have a program, and so let's suppose you have a program, and suppose that program is taking, suppose or the running time of the program is suppose n, or suppose 3n plus 5. So you have a program and running time of the program is 3n plus 5. Now for this running time, which is the actual running time that we have calculated, and as we have discussed that in asymptotic notation we are not going to worry about the actual running time. As I have also said, when this n goes very high, or when this n tends to infinity, this constant or this factor doesn't matter. Okay, so in this case, when we have the running time as f of n is equal to 3n plus 5, we can drop this constant, or we can drop this factor. As I said, this factor doesn't matter when this n goes very high, or if the number input size is very large, this factor doesn't matter. Similarly, this constant, which is like the multiplier of this n, also doesn't matter, because when this n is very high, this factor is like negligible, or this doesn't matter at all. So when we have this running time, that is 3n plus 5, we can say this, we can write this running time, or this time complexity of this program, in terms of big O notation, like big O of n. So when we have running time as 3n plus 5, we can say it is big O of n program, or this program is having complexity as big O of n. So as I said, we don't really care about the actual running time, we just care about this factor, that is the important factor for this running time. Okay, now when we say that the program has complexity as big O of n, so what is exactly meaning of this? So let's understand that by using this graph. Okay, so this red line is basically indicating the running time of the program, and I have written here as f of n. So f of n is basically running time of the program. Now we can say that the running time of the program, that is f of n, is nothing but big O of g of n. So basically we can say that f of n is big O of g of n, where g of n is nothing but a function. So in the previous case which we saw, we have written the running time of the program as 5n plus 3, sorry, it was 3n plus 5, and we have written that it is big O of n in terms of asymptotic notation. So in this case, this big O of n, in this case this n is nothing but g of n. So we can represent running time of the program in terms of big O notation, as we can say that f of n is nothing but big O of g of n. So in this case, f of n is equal to big O of n. Okay, and this thing, that is f of n is equal to big O of n, is going to be kind of true for all the value of n, or for all the input values which are greater than n0. So for some instances, for some initial instances, this is not going to be hold true, but for n greater than n0, that is the threshold value, for all those values this expression is going to be true. Okay, so this, when we say that f of n is equal to big O of n, so meaning of this is basically the running time of the program is never going to exceed k into g of n. So in this case, running time of the program is never going to exceed k into n, where k is a constant. So that basically means we are basically representing a upper bound for an algorithm. We are basically saying that running time of the program is always going to be lesser than this upper bound that we have drawn here by a blue line. Okay, so when we say we have running time f of n, and where f of n is equal to big O of g of n, so we are now representing running time in terms of asymptotic notations. We are not actually calculating the running time, so we are like writing it in terms of asymptotic notations. So when we are saying that f of n is equal to big O of g of n, that means this function, basically this program is not going to exceed greater than this time, that is k into g of n, where k is a constant. So in this case, when we say that f of n is equal to big O of n, that means running time of the program is not going to exceed k into n, where k is a constant. So that is very simple. That is a big O notation, and this is the mostly used notation. As we will go ahead and as we will explore some of the sample codes that I have created, and as we are going to analyze the asymptotic analysis, or as we are going to write the time complexity in terms of asymptotic notation, you will much betterly understand this notation. So let's go ahead and let's explore the next notation. We have the next notation, that is the omega notation. Now this omega notation is represented by this symbol, and omega notation basically represent the lower bound, and by lower bound we mean the best case. Okay, so as the big O notation used to represent the upper bound, this omega notation represents the lower bound. When we say that running time of the program, that is f of n, is omega g of n, that means the running time of the program is always going to be greater than k into g of n. As in case of big O notation, when we said that f of n is equal to big O of g of n, we said that running time is going to be always lesser than k into g of n. In this case, we are going to say, or we can say that running time will be always greater than k into g of n, as this omega represents the lower bound. And as I said, in case of asymptotic analysis, the base case is of no use for the programmer. So as a programmer, we are not going to worry about this omega notation. We should always worry about the big O notation. This is the mostly used notation for the programmer, or this is the best notation for the program. Let's go ahead and let's explore the next notation, that is the theta notation. Now this theta notation represents the tight bounds. Now by tight bound, what do we mean is, by theta notation we can get the tight bound, or we can get the range in which the running time of the program is going to lie. So in this graph you can easily see that this red line is basically representing the running time of the program, the actual running time of the program, and these two blue lines are basically representing the range in which the running time is going to lie. So this is basically the tight bound for the running time of an program. So this theta notation, basically when we say that f of n is equal to theta of g of n, that means the running time, the actual running time of the program is always going to lie between k1 into g of n and k2 into g of n, where k1 and k2 are constant, and this is going to be true for n greater than n0, where n0 is kind of threshold. For n less than n0, this expression or this thing may not be true, but for n greater than n0, this is going to hold true. Now in each and every case you can see that for n greater than n0 only these things are getting valid, or these things are valid. This is because, as I said, when n goes larger, this factor in the actual running time doesn't play any role. So if we have running time as 3n plus 5, when n goes larger, this factor doesn't play any role. That's why when n becomes greater than n0, or when n crosses some threshold value, this thing holds true. So suppose if I say that f of n is equal to theta of n, so in this case this n is nothing but g of n. So that means when we say that f of n is equal to theta of n, or time complexity of program is theta of n, that means the running time, or the actual running time of the program, is always going to lie between k1 into n, because in this case n is our g of n, and it is always going to lie between k1 into n and k2 into n. So this is kind of a tight bound for our program. So I hope you all understood the concept of asymptotic notation. This is a very important concept, and in each and every technical interviews, whenever interviewer will ask you to write a program, he will also ask you to tell you the asymptotic time complexity, or time complexity in terms of asymptotic notation. So you should always know the meaning of each and every asymptotic notation that we have. So let's just to recap, we have three asymptotic notations: big O, then omega, and then theta. Big O basically represents the worst case, omega represents the best case, big O represents the upper bound, omega represents the lower bound, and theta represents the tight bound. As a programmer, we should always worry about the big O notation, or the worst case. As I said, if you write a program which is running best for the worst case, then it is the best program. Omega and theta are kind of useless for the programmer. In some cases we also need to use these notations, but in general these are kind of useless, so we should always worry about the big O notation. Now let's see some programs for calculating the time complexity in terms of asymptotic notation, so that you will get an idea how we can calculate the time complexity in terms of asymptotic notation. So I have written some sample snippets. By these snippets we are going to see how we can calculate the time complexity in terms of, or how we can represent the time complexity in terms of asymptotic notations. So for the first example, I have written a simple statement, that is a is equal to 3 plus 2. Now this simple statement is going to take 1 unit of time, or it is the constant expression which is going to run in constant time. So in such cases, so basically when I say that calculating time complexity or representing time complexity in terms of notations, asymptotic notation, we are going to consider big O notation for this. Okay, so when I say asymptotic notation, basically I am saying that big O notation, because as I said, big O is something which is commonly used. So for this statement, it is always going to take big O of 1 time, because this is a constant statement and it is always going to take a constant time. This doesn't depend on the input. Okay, so that's why I have said that this statement is going to take big O of 1 time. So even in the worst case, in this statement there is no worst case actually, but that's why we have represented it as a big O of 1. This is something called as constant time complexity, because each and every time when this statement is going to execute, it will take the same time, or it will take this constant time. That's why it is represented something like this. We have a next snippet, that is a simple for loop, and for this for loop, as you can see, this for loop is going to execute for n times. So in such case, or for such case, we can represent this in terms of big O notation as big O of n. Okay, if you calculate the actual running time of this program, then you will get something like this. So let me show you that. So if we calculate the actual running time, then it will be, this for loop is going to so this assignment statement is taking 1 unit of time. These two statements are taking 2 unit of time, and they're going to execute for n plus 1 time. And this statement is taking 1 unit of time, and it is going to execute for n times. So the actual running time of this program is 1 plus 2n plus 2 and then plus n. So this is nothing but 3n plus 3. As I said, in asymptotic analysis, we don't care about this factor, we just care about the n, that is input. So we dropped all this and we can say that running time of this program is big O of n. So this is how we calculate the running time in terms of asymptotic notations. But as we can see, we don't actually need to calculate the running time and then drop the constants or drop the factors. We don't need to do that. We can easily say or we can easily understand this for loop is going to run for n times, and the maximum uh, degree of the polynomial that we are going to get is basically going to be n. So that's why running time of this program in terms of big O notation is basically big O of n. This is also known as a linear time complexity. Okay, so this is also known as the linear time complexity. These terms are very important, so you should always remember when the time complexity is only in terms of n, or the time complexity has n with degree 1. In that case we can say that the time complexity is a linear time complexity. Let's go ahead and let's explore the next code snippet. We have a for loop, we have a nested for loop. Now in this case, nested for loop case, the outer for loop is going to execute for n times and the inner for loop is going to run for n into n times. So the overall time complexity or the polynomial running time polynomial that we will get will have the maximum degree of n as 2. So that's why we have running time or the time complexity of this program in terms of big O notation as big O of n square, and this is something known as the quadratic time complexity. So we have this nested loop and we have time complexity of this as big O of n square. As if we calculate the actual running time of this program, the polynomial that we are going to get will have n square as the largest factor. So that's why running time of this program is big O of n square, and this is something known as the quadratic time complexity. We can also have time complexity something like this, that is big O of n cube, when you will have nested loops with 3 level, or with when you will have 3 nested loops, then you will have this complexity, that is big O of n square. This is also a quadratic time complexity. If you have 4 nested loops, then it will be big O of n raised to 4. This is also a quadratic complexity. If you have 5 nested loops, this should never happen, but in that case it will have big O of n raised to 5 time complexity. Let's go ahead and let's explore the another program. So we have a while loop, and this is a very standard algorithm that is called as a binary search algorithm. I'm going to discuss with you about this algorithm in next module, that is arrays, but right now just focus on this code snippet. We are not going to care about what is the logic behind this algorithm. We just need to calculate the time complexity. So we have this code, we have a while loop, and this loop is basically so let me just give you a high level overview of how this time complexity is basically coming as big of log of m. So let me go here and let me draw one array. Okay, so let's say we have this array and let's say we have these elements in the array: 1 2 3 4 5 6 7. Cool. So we have these elements. Now you must be knowing, or you must have an basic idea how binary search works. Okay. So let me write. We have 1 2 3 4 5 6 7. Let me add one more element to make it even. So we have 8 elements in this array. So when we have a sorted array, in that case we can apply binary search algorithm. I'm just giving you a high level idea. I just want to show you about the logarithmic time complexities. Okay, so we have this sorted array, and when we have the sorted array, we can use the binary search algorithm. Now the logic behind the binary search algorithm is basically when we have a sorted array, we are going to calculate the mid of that array. So suppose basically you are given a key that you basically want to find in this array. Suppose it is 2. So instead of going linearly and traversing entire array where the time complexity is big O of n, what we can do, we can apply an optimization, that is binary search. What we can do, we can jump to the middle element. So in this case, this is the middle element. We can check whether the middle element and key are matching. So in this case, it is not matching. We can check whether the key is greater than the middle element or it is less than middle element. If it is greater than middle element, then in that case we just need to search the key on this small array. And if the key is lesser than middle element, then we just need to search on this small array. So in this case, the key is lesser than middle element, so that's why uh, we are going to restrict our search to this short array. So we have this short array, that is 1 2 3 4. In this case, the middle element of this short array is this 3. It is not matching with the key, and the key is lesser than this middle element. So now we are going to restrict our search to this small array over here. So I can write the small array as 1 and 2. Now the middle element of this array is basically this 2, and in this case the key is matching with the middle element, and that's why we have got the answer, or we can stop over here. Now if you can see, we have originally 8 elements in the array, so we can say the n, that is size of input, is basically 8 in this case. And to search this key, that is 2 in this case, we basically need 3 steps. So you can see in 3 steps we are getting the answer. Okay, so such type of program or such type of algorithms are basically algorithms which are running in logarithmic time complexity, because if I say the time complexity of this algorithm is basically log n, so I can say the time complexity of this binary search is big O of log n. And why I'm saying it as log n, because you can see that when I say log, and in this case the n is basically 8, so when I say log base 2 8, it is basically 3. So in 3 unit of time, or in 3 steps, we are getting the output. Okay, so that's why such type of program where the input is basically getting divided log arithmetically, you can see that when we, in the first step we have array of size 8, in the second step we have array of size 4, in third step we have array of size 2. So basically our input is getting divided, or the input is getting restricted by log arithmetic size, or by we are basically dividing the input by a factor of 2. So in such type of program, or in such type of algorithm, the time complexity is a logarithmic time complexity, and in this case it is basically log n. Okay, so in this case the n is basically 8, so if I calculate log 2 of 8, then it is basically 3, and here also you can see that in 3 steps we are getting the output. So such type of program, so let's not go into the logic. I showed you by the kind of a demo, or kind of a representation, that how this binary search is basically working. So such type of program where the input gets divided by a factor of 2, such type of program have logarithmic time complexity. So in this case the binary search algorithm has big O log of n time complexity, and this is called as the logarithmic time complexity. We have one more complex algorithm, that is the quicksort algorithm, and this quicksort algorithm is having time complexity as big O n into log of n. Now when we will come to this algorithm, or when I will teach you this algorithm in arrays topic, I will explain you how this time complexity is basically coming. Okay, because as a when I need to explain this time complexity, I should also explain you this algorithm. So when I will come to this algorithm, I will explain you how this time complexity is basically coming. Okay, so right now just remember that for this quicksort, this is the time complexity. I'm going to explain you in further videos how we are getting this time complexity. Okay, so always remember, or this is the common sense, that big O of 1 is the best time complexity that we can have, then big O of log of n, then big O of n, then big O of n into log n, then big O of n square, then big O of n cube. These are nothing but the quadratic time complexities. So we always desire to have constant time complexity, then logarithmic time complexity, then linear time complexity, then this time complexity, and then quadratic time complexity. So as a programmer, you should always try to write to write a program where the time complexity will be in somewhere over here, in this range. If you are able to write a program which has the time complexity in terms of asymptotic notation in this range, then it is the good program. Okay, you should always desire, or you should always keep time complexities which are falling in this range. or you should always skip the quadratic time complexity, because as you must be knowing, when you have quadratic equation or when you have quadratic thing, the time grows exponentially. So as your input will grow, the time for that input will always, or that will also grow. But when you will have linear time complexity, the time complexity or the time required for the program will grow in the linear fashion as the input. So we should always desire such type of time complexities. Now it was enough discussion on this topic. Let's let's solve some practice problem. Let's solve some problems. So let's take this first problem, and so I'm going to solve the first problem, or I'm going to solve the first two problems, and I'm going to give you this problem as an assignment, or as an, yes, as an task, and maybe I will, if I will tell you its answer in the next video. So let's see how we can calculate time complexity in terms of asymptotic notations for this program. Okay, so this is a nested loop problem. Okay, we just need to care about the factor of n. We don't need to care about this constant statements. Okay, so we just need to care about how many times, or what is the highest degree of the polynomial going to be. Okay, so this outer loop is going to execute for n times, and so this j is basically starting from n. So let's assume that n is 5, so j is getting starting from 5, and when I is basically 0, so when I is 0, this loop is going to execute for 5 times, that is this loop is going to execute for n times. So the maximum, at max, this loop is going to execute for n times, so n into n, that is basically n square. So this is the maximum degree that we are going to have for this polynomial, or for the actual running time of the program. So we can say that this program is going to run, or this program is going to take big O of n squared time. So this is something, a quadratic complexity. I hope you got this. So when you have a nested loop, and when the outer loop is running for n times and inner loop is also running even in single step for n times, then it is n into n, that is n square. So this is a quadratic time complexity. Let's see what is the time complexity of this code. So we have a is equal to 0, we have I is equal to n. For I greater than 0, we are like doing a is equal to a plus I, and then we are dividing I by 2. Okay, so let's assume that n is suppose 6. So in step 1, I is basically 6. In step 2, I is basically going to be 3, and in step 3, I is going to be 1. In step 4, I is going to be 0, and we are not going to enter in this loop. So basically when we have n as 6, we are just going through this loop 3 times. Now this 3 is nothing but log 6. So we can say that this program is basically running in logarithmic time. So I can say that this program is having time complexity as big O of log of n. Always remember, when your input is getting decreased or is reducing by factor of 2, you will get time complexity as log of n. Always remember this. So even in this case, this I is basically reducing by factor of 2, or it is getting divisible by 2 in each and every step. That's why the problem size is getting decreased logarithmically. That's why the running time of this program is big O of log of n. And now let's come to the assignment question to you guys. So this is the question that you all are going to solve. So we have a is equal to 0, b is equal to 0. We have one for loop which is running for n times. We have another for loop which is running for n times. So let's take a moment. Maybe you can pause the video over here, and maybe I can tell you answer of this question immediately after this. So just pause the video, think on it, that how you can solve this question, and I will reveal the answer. So I hope you have got the answer for this question. So this for loop is basically going to run for n times, and this for loop is going to run for m times. So we have two inputs on which this program is basically depending, n and m. So that's why the running time of this program, or the time complexity of this program in terms of big O notation, is going to be big O of n plus m. This is also a linear time complexity. I hope you are clear with how we can calculate time complexity in terms of asymptotic notation and in terms of big O notation. I hope you got all the concepts that we have covered in this video, and I hope you enjoyed this video. Thanks for watching.